Hello everyone, this is NK, and in this video I'm going to be going through a presentation on the paper Attention is All You Need. I'll mainly be focusing on the model architecture, but however we're also going to go through briefly on an introduction and abstract of the paper, and we're also going to talk about the results from this paper. So the problem statement. The main goal of this paper was to carry out sequence transduction for machine translation, and the specific task carried out was translating from English to German and from English to French. And the core idea here was to remove recurrence and convolution and to use only self-attention to model dependencies. And this is because previous models usually used self-attention with convolution layers or recurrent neural networks. However, the goal of this paper is to eliminate the need of recurrent neural networks or convolution layers and use only attention layers. And the paper claims to have achieved a simpler architecture which enables parallelizable training and a strong translation performance. So taking a brief overview on the model architecture, we have encoder-decoder stacks, in this case 6 encoders and 6 stacks of decoders, made up of the encoder, self-attention and feed-forward networks, and the decoder or max self-attention, encoder-decoder attention and feed-forward networks. And each of these sublayers uses residual connections and layer normalization, usually to stabilize training and avoid vanishing gradients. And as you can see, the architecture is fully attention based, which makes training parallelizable and more efficient. And taking a brief overview at the image here, you can see we have input embeddings over here, carrying out positional encoding. And also we can see the multi-head attention layer here and the feed-forward network. You can see the residual connection that moves from here to here at every stage, and you see the multi-head attention and feed-forward network. And this is at the encoder, and the decoder as well has a similar structure. However, it adds this max multi-head attention over here, but pretty much the same with the output linear layer and softmax activation, which returns the output probabilities. So looking at some of the main features, you see the first one we had looked at was the positional encodings, and these are important because they add token order. So positional encoding adds token or word order, so this information is not lost in computations, and it ensures that word positions in a sentence are maintained. So pretty much any sentence, this is a good day, ensuring that when you encode these words and pass them through all of these computations, that the order of the words still remains even at the end of the day. And you can see the formula on the right here using sine and cosine functions. And over here we can see a little bit of what happens in the attention layers. So this formula here gives us a little bit of it. Attention carried out on Q the query, K the key, and V the value. It simply must a softmax function looking like this, where you have a product of Q by K, the transpose of K, divided by the dimension of K and multiply that by the values. And we're going to go a little bit in depth into what this means, but before that, just want to say that if we take, for example, a sentence that says I love football, then just for the purpose of understanding, we could encode the words I love and football like this: 100, 010, and 001, and we could initialize our Q, K, and V matrices as this. And just a quick note that this is not how these matrices are initialized actually in the model, but this is just for a little explanation. And so actually what happens in the background is you have this the product of Q and K transpose, which gives relevant scores. So we multiply, for example, the Q here, the query could be the word I, and we multiply that by the keys, in this case every other word. So I love football, the other words. And so we carry out the matrix multiplication of the query and the key, and then we scale that to stabilize gradients and for large dimensions as well. And you could pass that through an optional layer here, but if not, that is passed to the softmax function, which converts scores to attention weights, as we see over here. And these weights are added to the values V to produce our output, as you can see here, another matrix multiplication. And multiplying these weights with the values makes the model understand how much attention each word should pay to the others. So pretty much that's what happens in a single attention head. However, for the model architecture, multi-head attention is used, and simply put, it's just a stack of individual heads. So like we saw before, what happens in a single head, multi-head attention just stacks multiple heads together, concatenate the results from that, and then passes that through what a linear layer, and then goes through the same process like we saw before. So if we go through a final overview of our encoder and decoder layers, like you see here, this is our encoder, and here we have a decoder. And the encoder, simply put, contains a self-attention layer which passes its results to a normalization layer and then to a feed-forward network, and the results from the feed-forward network are normalized as well. So like we said before, we have our input sequence which is embedded, and positional encodings are added to it. These are passed toward a multi-head attention layer, and after that the results are normalized and residuals are added, as you can see over here, and the results from that sent to a feed-forward network whose results are normalized as well, and residuals added, and the results from these are sent to the decoder. On the decoder, the only difference between the decoder and the encoder is that it has a max self-attention layer, and the purpose of this is to prevent attending to future tokens. So say we are predicting the next word, we want to be able to focus on the previous word and not look at any word in front. And here we can see the results from this model architecture, and the model performs better than previous benchmarks based on the WMT translation task. And you can see the model scores over here. We have a binary model, convolution sequence to sequence, multiple models over here which were previous benchmarks. And you can see the performance of the transformer, the big and the base model. But the base model already performs better than the others here, but the best performance is a big transformer model here. And it also has the best performance translating from English to German and from English to French. And in conclusion, attention-only models replace recurrence and convolution in many natural language processing tasks, and it provided some key advantages like parallel training and efficient long-range dependency modeling. And these models have also been the foundation for some models like BERT, GPT, T5, and most of the transformer-based models of today. Thank you.